Alright guys, logistic regression. So logistic regression, it is a form of a supervised machine learning technique, which means your dataset will contain the input and its corresponding ground truths. Means dataset will look something like this. You have your dataset, it has pairs of x and y's. So yeah, you have this. And I can build from 1 to, let's say, n, because let's say the dataset has n samples, hence n. I'll go from 1 to n. Now, logistic regression is used for classification tasks. It is used to solve some classification problems. And specifically, we solve binary classification problems using logistic regression. Binary classification means it has two class. Binary means two. So we are dealing with only two classes, like dogs versus cats, or let's say dog or humans. And in this case, also exists a function that describes the dataset, the relationship between the x's and the y's, and that usually maps from Rn to some discrete values, which is 0 and 1. So this is the ground truth, takes only two values, which is 0 and 1. That's all it means, right? So now comes to the hypothesis function. So in linear regression, if you remember, the hypothesis in linear regression was W transpose X, where X is the input. That was the hypothesis function for linear regression, right? And this one, so in case of linear regression, this will belong to the real number. This will give an output that will belong to the real number, means the range will be from minus infinity to infinity, but we want only discrete values. We want it to be in between, at least in between 0 and 1, if not exactly 0 and 1, right? So for that, what we can do, we can simply pass this entire thing to a sigmoid function, right? Sigmoid function basically is nothing but something defined by this formula, which is minus z. Yeah, so this is my sigmoid function. Travel drawing, yes, nice. So if you look at the graph of sigmoid function, then that will look something like this, right? So this is your y equals 1, this is my 0, and this is your 0.5, and this is my x, and that is my y. So this is the graph. So what this will do, sigmoid will map your real number, any real number, it will map that in between 0 and 1. It will map the whole real number to a number between 0 and 1. So that's all we need. Hence, we're passing this entire thing to the sigmoid function. And this, ladies and gentlemen, this is our hypothesis function, right, for logistic regression. Nice, brilliant. So the next thing the next thing that we need to discuss is cost function. So the cost function, because we need something that will tell us that how far our hypothesis is from the actual target function. So that will be determined by a cost function. Unlike in case of linear regression, we use something called BCE loss. It stands for binary cross entropy loss. Now it is defined as, loss is defined as y hat, which is the pred, actually y, which is the ground truth, sorry about that. So y is the ground truth minus of y, the ground truth, times log of y hat, which is the prediction, minus 1 minus y, which is the ground truth again, times log of 1 minus y hat. So this is my BCE loss, right? So this is for only one sample. This is for one sample. Now if you want to take the whole dataset into consideration, then just take the mean of it, which is basically nothing but expectation of this whole thing, right? I mean, sum them up and then divide that by the number of data points rather. So that is our BCE loss. Now the next thing is we have to find out what gradient updation step, right? So we have our weights. This thing is also a weight, right? So we need to update this. We need to find the max, like the optimal set of weights, optimal configured weight that will help us to separate the two classes that we are hoping to separate. So this is our weight updation step is similar to that of linear regression. So this is same as like eta is also, this is nothing but the learning rate, then del L by del W. So for a specific W, if you want to update a specific W, then you have to differentiate the whole loss function with a specific W, right? So let's just go ahead and find out what this expression will be. This bloody expression will be, right? Which means del L by del W. All right. So y hat, let me just remind you, y hat is nothing but sigmoid of W transpose X, right? And we will write this in this way, like sigmoid of Z, where Z is W transpose X, right? Now we are good to go. So del L by del Z. We'll first compute the derivative of the loss function with respect to Z first. So what this will be nothing but del Z of the entire expression. Entire expression is what? Log of sigmoid Z, right? Minus 1 minus y, then what? Log of 1 minus sigmoid Z. Brilliant. Now differentiate this whole thing. What will it be? Y is nothing but a constant, it will come out. So this one, log of something, is 1 by, sorry, not x, this will be z, sorry about that. Now differentiation of sigmoid function. So well, f dash of z will be sigmoid function itself and 1 minus sigmoid of z. If you differentiate this entire thing with z, then this will be the result, right? And if you want, then you can just simply go ahead and check it out, but just for lack of time, I'm just in a hurry, so I'll just simply compute this result. So this will be my z and 1 minus z, right? Done. This entire thing is nothing but a constant. This will come out, which is 1 minus y. And this thing, again, same thing. It's 1 minus sigmoid of z. And this entire thing, oh shit. Yeah. So this entire thing, if I differentiate this with respect to z, then this will go to 0, minus, so minus, then this thing will be z times 1 minus sigmoid of z. So there is a minus over there. So one thing you can see, this get cancelled, and this minus and minus, it will multiply and it will make it a plus sign, and here this get cancelled. So basically ultimately it boils down to this expression, minus y and this one, plus I have 1 minus y, and then 1, this will be what? This will be my sigmoid of z. That's it, right? Yes, absolutely. So this is my expression. Now I can just simply open the brackets. So if I do that, then I will get 1 and plus y sigmoid of z. This is what? This is my sigmoid of z and minus y sigmoid of z. Wow, nice. Holy shit. Yeah, so this thing and this thing get cancelled. So what I will get? Ultimately, this thing boils down to sigmoid of z minus y. Sigmoid of z is nothing but sigmoid of w transpose x minus y, and this end expression is my y hat minus y. So del of L by del z will be my y hat minus y. That's clear for sure. Now next thing, we have to find out del z by del w, right? Oh, poor handwriting, sorry about that. So del z by del w. This will be what? Summation of xi's and wi's from 0 to n, right? Small n, let's go for small n, yeah. Which means this is my x0 w0 plus dot 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 xn wn, right? Now if I do differentiation with respect to a w naught, let's go for w naught. Then a rest will be considered as a constant, so the rest will be treated as constant since we are computing the partial derivatives. Only this will be taken into account, so which means dz by del w will be nothing but x naught. Similarly, del z by del wn will be xn. So basically, to generalize this thing, del z by del wi will be x of I. So ultimately, del L by del Wi, this will be nothing but del L by del Z by del Wi, multiplication, chain rule. So this thing we know, this expression we know, which is nothing but the difference between the parades and the response, the ground truths, multiplied by the corresponding axis. So this is what my del L by del W is. So my gradient updation step will be, if I want to update Wi, this will be my Wi minus eta will always be there, and multiplied with this entire expression. Next slide. Alright, so this is my learning rate. This is my LR, learning rate.